Welcome back to the YouTube channel Ruhan Pargov. I'm Ruhan Pargov, and today, basically, I wanted to take the concept of magnetism, mainly electromagnetism, and see how it's really applied in the real world, as I have discovered from my schooling experience that a lot of the times electricity outshines magnetism, where both of them are equally necessary for the other to work. So today we're going to talk about applications of magnetism and in specific particle accelerators. So moving on, I want to ask you a question. If you think about manufacturing and customizing semiconductors, basically the small transistors that are inside your CPU about the size and scale of 2 or 3 atoms, or if you think about something like medical imaging in the form of X-rays, CT scans, MRIs, and stuff they use to inspect your inner body without cutting you open, or sterilization and disinfection of edible products, but also medical products, which requires a lot of energy concentrated to kill the bacteria, and last but not least, the research of subatomic particles in the quantum world. What do all of these things have in common? Well, if I told you that all of them are another use of particle accelerators, I would not be wrong. So before you start to understand how they work, let's look at what really is a particle accelerator. Well, a particle accelerator, like it sounds, takes a lot of charged particles. In this case, we model them using protons. It then places them inside a vacuum where they remove all the air because, as you can guess from the name, particle accelerators accelerate particles, and because these particles are subatomic like protons, electrons, the existence of air is a large hindrance to them. And then the particles are then accelerated by the use of opposing electrical fields. Basically what that means, as you can see in this short animation, is that the proton is pushed upward using the negatively charged fields. As you know, negative and positive attract, opposite charges attract. However, once it reaches that midpoint, the bottom 2 negative charges switch to positively charged plates, which then push the particle upwards while the top ones are still pulling on it. And then the top one switch to positive, which provides this continuous cycle for many and many protons to go through. As you know, particle accelerators, they're not really accelerating a singular particle, they're accelerating a chain of these singular particles. Last but not least, electromagnetism is then used to steer these particles. So basically, because we're talking about particles that need to be accelerated to almost the speed of light, we need there to be a place to turn, right? Because the longer you make the tunnel, the harder it is to keep it straight. Also, we're ignoring the curvature of the Earth, as like some of these particle accelerators, the biggest of them in the world, are around 29 miles long, and making them straight would just not be feasible. So we need something which can allow these protons to turn. And if you just keep them straight and there's a wall and they collide and then turn, the particles lose energy. And every time they lose energy, the more work needs to be done to add that velocity back. Now let's discuss this in more detail. But before we do that, we need to learn a little bit about Lorentz Law. Now, Lorentz Law is about how magnetic field interacts with charged particles. Basically, anything that has a positive or negative charge interacts with the magnetic field. Now, the interesting thing is a magnetic field never does any work on the charged particle. What I mean by that is the force applied to that particle is always perpendicular to the direction of the magnetic field, and the velocity, basically the change in velocity which is induced, is also perpendicular to both of those previous measurements, as can be seen in the right-hand rule. Now, why is that important? Because what that means is that a magnetic field does not accelerate the speed of a particle. It never does any work. However, it does change the direction of travel of these particles. Now, let's look at that in a little bit more detail. Here you can see a paper with a magnetic field on it, and the small crosses basically mean that the magnetic field lines are pointing towards the paper. The field is going away from you. Now in this case we have an electron, so the right-hand rule needs to be modeled the other way around. So basically, using the right-hand rule we saw before, we put our force finger towards the middle of the paper, because as we learned, the force is always perpendicular to the magnetic field and the velocity is perpendicular to both. So in this case, if you do this theorem, you basically see that your index finger is pointing towards the paper because that's the direction of the field. Your force is pointing downwards, and your particle should have a velocity towards the left. Now in this case, the velocity to the left would mean the positively charged particle is to the left, therefore the negatively charged particle will go to the right. And that is basically the essence of how you use Lorentz Law and how charges interact with the magnetic field. And it causes centripetal motion, which some of you might be familiar as also the motion which causes the Earth to rotate around the Sun. Basically, it's the idea of orbiting, and the thing which causes the Earth and the Moon to orbit. Now, let's go to how magnetic fields are applied inside particle accelerators to gain a better understanding. Now, in this case, I want you to imagine that in the image there, the radius r is basically the start of the magnetic field, and therefore the centripetal motion will act around it. So that's sort of your leverage. And the origin of r is the origin of the uniform magnetic field. And in this case, I have a short question for you just to test your understanding. In the direction v, as stated, and the particle is the proton. So the direction of v is the direction which the particle is going. And also, instead of an alpha particle, let's just assume it's a proton because that would be easier to model. And the direction of current does not need to be changed because it's a proton. It follows conventional current. I want you to see what's the direction of the magnetic field to allow for this particle to turn. And I'm pretty sure you'll need a little bit of this. So pause the video here if you want to try, but let's move on to the actual analysis. So in this case, what we want to do is sort of take the information we have. We know that the magnetic field, in this case represented by the blue, will be pointing towards R because it's that's the area of the field, and we know the direction of the motion is towards up. We make sort of a gun shape using our middle finger, and the magnetic field, basically our index finger, must point towards the paper. Now let's see that in more action. Let's see how this right-hand rule transforms, these vectors transform. So as the particle moves, the vector would basically go up and around and through, and that would show us that our magnetic field must point into the paper, marked by the yellow cross. And here we can see that, and that is basically a magnetic field that will allow it to turn. And this magnetic field is just created using simple electromagnets, very strong ones, that one is placed, basically the north pole must be placed above the pipe and the south pole must be placed below the pipe for the magnetic fields to go through the pipe into the south pole. And that is basically all the sources I used. Particle accelerators are very fun. This is an image of the collision zone of the Large Hadron Collider, the biggest particle accelerator in the world. It's about 29 miles in circumference. It's absolutely huge. The technology used is insane, and I would encourage you to read up more on this. Thank you very much, everyone, to whoever listened through the whole video. This has been Ruhan. I hope you enjoyed it. If you did, please leave a like. Please subscribe. If there are other people in your life who are interested by scientific content, please recommend this video to them. And yeah, more videos in the works soon. I really think you'll enjoy the next one. It's a video essay on some of the ethics and stuff about research. It's a unique video. I'm pretty sure you haven't found it anywhere else on YouTube. This is what the YouTube algorithm wants you to watch next. This is what they want you to watch next from my channel. Thank you very much for listening, and peace.